Welcome to Everything You Wanted to Know About RDMA, but Were Too Proud to Ask, a webinar presented by the SNIA Data Storage and Networking Forum. My name is Eric Smith, and I'll be your host and moderator for today's webinar. I'm pleased to introduce you to our expert speakers, Mikhail Calderon, a distinguished engineer and software architect at Marvell, and Rohan Mehta, a senior software engineer at Microsoft. Before we get into the content, I wanted to provide a quick overview of the SNIA community. SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. SNIA is comprised of 200 industry-leading organizations, 2,000 active contributing members, and 50,000 participating IT end users and technologists worldwide. The SNIA Data Storage and Networking Community, also known as the DSN community, is an active group within SNIA that provides vendor-neutral education and insights for applying network storage standards and associated technologies to a broad spectrum of end-to-end solutions. Now, some logistics for today. The slides for this session are available under the Attachment tab at the bottom of your console. If you want to ask a question during the presentation, you can do so by selecting the Ask a Question option and entering your question there. All questions asked during the webinar will either be answered live or as a part of a question and answer blog post that we try to post no more than 2 weeks after the webinar. Please take the time to rate the session and ideally leave a comment, even if you need to leave early for some reason. And this is because we take your feedback very seriously because we greatly value your time and we want to make sure you're getting the most out of each session as possible. Now, if you want to interact with people like the presenters of this session and other industry professionals, consider joining SNIA and the DSN community. We meet every week on Thursdays at 10 a.m. Eastern. Finally, I wanted to call your attention to the SNIA legal notice. This provides SNIA's copyright notice regarding the use of the material. SNIA is not providing any legal advice, and there are no warranties expressed or implied. So if you want to reference this material, please do so at your own risk. And with that, I'll hand it over to Rohan to walk us through today's agenda.
Thank you, Eric. Hello, everyone. My name is Rohan. For today's agenda, we'll start with covering a brief overview of what RDMA actually is, a little bit of history, and a quick overview of how RDMA works. Mikhail will then deep dive into the technical details of what are the key elements required to write an application that can communicate over RDMA, along with some sample traces for each of those elements. Finally, we'll discuss about some use cases of RDMA in today's world, with some focus on storage protocol stack and how RDMA has integrated into it. And then we'll wrap it up with key takeaways. So I'm going to start from the very beginning here. What is DMA, or direct memory access? It's a mechanism that allows data transfer within a device between an I/O peripheral and a memory without involving any CPU. This is usually done with a very specific type of a microcontroller or a chip on the I/O device. It's called a DMA controller. Some example applications that use DMA controller today are, say, storage controllers, which use DMA controllers to transfer data between storage devices and main memory. GPU also uses DMA controller to transfer data between GPU and main memory. Even some printers and scanners use DMA to do their task. DMA controller is not a new chip per se. It's been there for a very long time with the goal of freeing up CPU to perform the actual computing task. Now we know that a NIC, or network interface card, is usually the primary device that facilitates communication or data transfer over a network. So when NIC becomes this I/O device or I/O peripheral with a DMA controller on it, the mechanism becomes RDMA, which is remote direct memory access. And so you now are allowed to do data transfer from one remote server on a network to another remote server without involving CPU at either end. And like with typical networking communication models, we try to standardize the language in which we communicate over the network. And so that becomes your protocol stack. You define what the layers are, what the semantics are within those layers in the protocol stack, and you give a name to them. And so each protocol stack, we have like 3 or 4 major RDMA protocol stacks, InfiniBand, IWARP, RoCE, which we will discuss more later in the presentation. Key benefits of RDMA include or start with zero copy networking, which allows NIC to transfer data from our NIC directly to the application memory space or vice versa. Thereby you are eliminating the need for any intermediate copies in the kernel networking stack, such as socket buffers. The way this happens usually is, you make memory pointers from the RNIC's memory buffer pool available to the application memory space. And we will talk more about the details of how RDMA works later in the presentation. All of this involves no work done by CPUs, caches, and sometimes even no context switches, depending on, whether your application is already in kernel mode or not. And this transfers can continue, the data transfer can continue in parallel with other system operations. All of this happens at almost the hardware line rate, so it leads to very low latencies and very high throughput. So in this slide, this is more like a quick sales pitch of some performance characterization done for a 40 gigabit Gbps network link between RDMA and TCP back in 2015. Things are much faster now, but the essence is still the same. The benefits that RDMA has over TCP are still there. RDMA, you can see that RDMA delivers consistent line rate of throughput and very low CPU utilization by almost 65% compared to TCP, particularly for small IO sizes. RDMA benefits from low jitter and no throughput collapse, so it's very consistent, unlike TCP. The latency comparison also very drastic. We can see up to 88% improvements for 2 KB IO size. This difference is done for 2 KB IOs, but the order of the difference remains about the same, so around 35 to 65% for larger IO sizes of the order of multiple kilobytes or even megabytes. There were more experiments done later, and you can read more about this in the paper that's highlighted below. Taking a brief look at the historical timeline of RDMA, as mentioned in the beginning, the concept of DMA is as old as that of computer architecture or the first x86 microcontrollers. But the concept of RDMA was theorized early 90s and researched thereafter. The InfiniBand Trade Association was formed in 1999, and InfiniBand architecture specification, the first version was released in 2000, which is where they introduced the layer 2 to layer 4 semantics unique to the InfiniBand transport protocol. InfiniBand gained some traction during those time, particularly in the high-performance computing, the HPC industry. Some high-frequency trading firms were the early adopters, but they didn't scale well in the sense, especially when compared with how ubiquitous the TCP, IP, and the Ethernet network architecture is. InfiniBand required an entirely unique stack pertaining to InfiniBand layer 2, InfiniBand layer 3, InfiniBand layer 4. And so this led to development of something called RDMA over Converged Ethernet, or RoCE. This RoCE was developed in 2010, and RoCE v2 came in 2014. And they offered improved performance, but over existing Ethernet-based data center fabrics. This led to very rapid growth in RDMA adoption in data centers during the second half of the last decade. NVMe over fabrics further drove the adoption of RDMA because NVMe over fabrics over RDMA led to the growth of RDMA adoption in storage data centers as well. We all know RDMA continues to evolve today as well, playing a key role in all AI ML applications, high performance computing, cloud computing, and so on. I wanted to pause and talk about in one slide what message passing programming model is. It's a relatively simple concept. Message passing in distributed systems is crucial, very important to guarantee safe, effective, and dependable transfer of data between distributed nodes or distributed processes over a network without the need to share any resources on either side. Some examples of message passing models include IPC, or inter-process communication, gossip protocols, concurrency mechanisms, etc. So because message passing model is usually transparent to the underlying transport layer, the layer 4, RDMA applications can fit right into this design. So you can have RDMA applications running in distributed systems, distributed environments very easily. Standards like MPI or message passing interface have made it even easier because MPI covers layer 5 and above in the OSI network model, thus providing a full stack of RDMA compatible applications. In summary, it's essentially you can swap out any transport protocol, any RDMA transport protocol, but your overlying RDMA application can still function as is. How does what's the difference between how RDMA works and TCP works? So TCP, let's take a quick look of how data flow is happening over TCP. You can see that the sender application has to post its data into the operating system kernel and its TCP IP stack, which in turn packetizes that data into required IO sizes, orders it, and indicates to the NIC that when it's ready for transmission. The packets then go via the NIC on the wire to the destination. And on the destination side, the same thing happens, but in reverse. The destination typically uses an interrupt-based approach to read each packet, copy the contents in the local socket buffer, stream it into the TCP IP stack inside the kernel, reordering, doing some post-processing, waiting for any failed or missed packets, and then finally making that data available to the application buffer. At each of this step, a lot of CPUs utilized because a lot of per packet level processing is happening, as well as a lot of copying of this data is happening at each of the layers. If we scale the scenario out in a distributed system, the traffic would involve, typically done over HTTP protocol, and each write or read command will have to go through similar packetizing and segmenting on the source, as well as reordering and re-requesting of failed packets and coalescing of failed packets of all the packets on the destination. RDMA takes away all these intermediary layers. So what you now are able to do is have the application's memory and the RNIC or the RDMA capable NIC talk to each other directly, thus bypassing the whole networking stack and the whole operating system that comes where the networking stack lies in between. Since most of the networking stack is in the operating system kernel, we also sometimes call it kernel bypass. It depends on how distributed your application is. You could actually end up saving as many as 3 copies of data just to send your data from application to RNIC out of the server, and same thing on the destination side. Because of this, a networking stack usually resides in the kernel. Sometimes kernel bypass is also touted as the benefit, and this benefit is available to both the sender and the receiver. So this is just a side-by-side comparison of how TCP behaves versus RDMA. There are multiple layers involved in TCP of the networking stack, but there's an option to skip all of those layers when trying to talk over RDMA. Mikhail?
Yes, thanks, Ron. So now let's dive into the technical details of RDMA and see how it actually works. So in the next few slides, I'll talk about the RDMA operations, the RDMA objects used to communicate with the RNIC, how a connection is established, the API of write for writing an application, and how RDMA actually looks on the wire. So I'll start with explaining the RDMA operations that we support with an RDMA NIC, and we'll separate them into 2 groups. There's the channel semantics operation, which are the send-receive. In this case, both sides are active, server and client. And the sender sends a message to the receiver without actually knowing where the data is going to be placed on the remote side. And the receiver needs to perform a corresponding operation to make sure it can handle this incoming data when it arrives. When we talk about the memory semantics group, this is the read, write, and atomic operation. And this is where the RDMA CPU kernel bypass comes in. In this case, the RDMA NIC can read data from remote memory into its local memory without the remote CPU even waking up and doing any work or processing. Same idea for write. It can write the data directly to a specified location in remote memory and perform atomic operations which are necessary for synchronizing when running distributed applications. So how do these RDMA operations work? Or how can the application actually do them? It uses the RDMA main objects, which I'll talk about now. So an application uses an RDMA API to communicate with the RNIC, and the main objects that it uses are a QP, a CQ, and a memory region. There are more, but these are the main ones which I'll talk about now. The Q pair, which is the first one I'll go into, and we will go later on into the CQ, which is the completion queue, and MR, which is the memory region. Q pairs are used by the application or also by the RDMA NIC consumer to submit operations to the RNIC. So the operations, as I already mentioned before, the send receive or the read write and atomic operations. It consists of a send queue and a receive queue, but this is not the same as the send and receive operations. The send queue, the SQ of the QP, is used to post operations to the RDMA NIC, either the read, the write, or the send or the atomic. And the receive queue is for posting the buffers to accept remote send operations from the other side. Now, every application can have several queue pairs. It can use them for parallel processing when required. For example, if you think about full cluster connectivity, you want multiple applications to communicate with different nodes in the server. They'll have multiple QPs, and they can communicate this way in a full cluster. And what an application posts to the queue pair is what we call a WOOKie. It's a work queue element. And a work queue element consists of a lot of parameters, but the main ones are the operation code, the address where it wants to read and write from, and remote address of where it wants to read and write to. And of course, you'll have the length, and that way the RDMA NIC will know what it wants, what the application wants to do. So these are the queue pairs. Now moving on to the completion queues. So the completion queue is the way for the RDMA NIC to notify an application that the work request that was posted on the QP is completed. Similar to how an application can have several QPs, it can have several CQs. And the SQs and RQs of a queue pair are mapped to either the same CQ or different CQs. You can have a single CQ that serves several queue pairs, and the mapping between queue pairs and CQs is not a one-to-one mapping. When an application wants to read the CQEs from the CQ, it has two methods for processing the completions. So the first method is a polling mode method, where the application just does sort of a busy loop on the CQ, reading the CQ elements and checking what was completed and with which status. This is good for when you want low latency and high throughput, but it is, of course, CPU intensive because you're in a busy loop reading the CQs. The other method is an interrupt-based mode, where this, of course, reduces the CPU usage because you're now reading the CQ only once you get an event. You register a request to the RDMA NIC to notify you once there's new information on the CQE. So these are the CQs, completion queues. And now we're moving on to the memory region. So a memory region is an area of the memory that's registered with the RDMA hardware so that it can enable direct access for data transfer operations. So when you register a memory region, you actually provide the RDMA device, the RNIC, with the necessary permissions to read from or write to this memory. So an application registers the memory, then this memory is pinned to physical locations that is accessible to perform the DMA by the RNIC. Once you register a memory region, the RNIC will return an L key and an R key identifier. So the L key is the local key and the R key is the remote key. And these are used by the applications to notify where you want to read or write the memory to. So the RNIC, given an L key or an R key with an offset and a length, will identify the exact location where it needs to write the data to. Now, when you post a WOOKie, the work queue element, on a QP, it will consist of an SGE list. So these SGEs will actually can point to different memory regions and different offsets inside the memory region. So if we see on the drawing here, we can have two SGEs pointing to MR1, which is referencing the first buffer, and MR2, which references the second buffer. And the ability of separating these SGEs gives the flexibility to allow RDMA to handle like complex data structures and optimize the communication performance. So these three are the main objects. Talk about a few more interesting ones. So the protection domain. A protection domain is a logical entity, and it's used to manage and control access to various RDMA resources. So it actually groups objects that can work together. Right? It's associated with like a QP and an MR, for example, that were created. Once they're in the same protection domain, the RNIC needs to validate that if a command was received on a specific QP to write to a specific MR, make sure that they're on the same protection domain. And if they're not, it fails the request and provides a completion error. And another object I want to talk about is the SR queue, which is the shared receive queue. The shared receive queue is used by QPs instead of a receive queue. So in the beginning, when I talked about a queue pair, I said it has a send queue and a receive queue. But you can also create a queue pair that doesn't have its own receive queue, but uses a shared receive queue. This is used for more efficient memory handling and consumption, where not every QP has its own receive queue with RQ buffers. And it can also provide simplicity in terms of not handling multiple receive queues when you want to check which data has arrived. So it can make that simpler. So that wraps up the main objects of QP, which I will talk about more in the slides when I go and show how we write an application. But before that, I'll talk about the connection management. So I said a QP is an object, and it's the object that is used by the application to communicate with the RNIC, but it's also a connection. So if you take two Q pairs on each one of sides, so you have two pairs with two QPs, when they talk together, it's like a peer-to-peer connection, which is a reliable connection. So there are four types of QPs. There's a reliable connection. This is somewhat comparable to TCP, okay, where you have the reliability and you know that whatever you send will arrive on the other side and acknowledgements and so on. There's an unreliable connection, which is, as its name refers to, unreliable, meaning that some packets won't necessarily arrive, can be used for like video streaming and things that aren't critical for every packet to arrive. Reliable datagram and unreliable datagram. So the unreliable datagram is somewhat comparable to UDP. On a reliable connection, all the RDMA operations are supported. And for unreliable datagram, for example, only send is supported. The connections are established out of band for InfiniBand and RoCE. This means that you have a dedicated Q pair, or you can use any other mechanism you want to create a QP connection. You just need to make sure that both sides get enough information so that they can then start sending RDMA packets with all the necessary parameters to communicate. Every wire protocol will have a different scheme for initiating a connection. You have the InfiniBand and RoCE and iWarp, which works over TCP. But because it's out of band, you can also simulate a connection setup using emulated using just plain sockets. XRC is an extended reliable connection. This wasn't part of the initial InfiniBand specification. It's an annex added later on. And it's a method of allowing significant savings in the number of Q pairs that are required for full large cluster connectivity. In XRC, you don't need every process to have a communication to every other process. You have one single XRC initiator QP that can communicate with all the processes on the remote node, and this reduces the overall number of connections in your cluster by a factor of the number of processes. Let's see how this looks in an image. So with RC connection, say I have two nodes with three processes on every node. I want every Q pair to communicate with every process, so I need a connection for every process on the second node. So as you can see here, the overall number of Q pairs in this example, for example, will be the number of nodes times the number of processes times the number of processes, right? This brings us to 18. With XRC, we'll go to the next image. And now this image just shows one direction for simplicity, but think about it as symmetrical. Okay, so so both sides, node 1 will also have the same receive QP to SRQ association. So here the receive queue is actually not part of the process. It's created outside within an XRC domain and can be attached to by other processes. And when QP1 will send some request to node 2 QP3 receiver, then it will be able to multiplex the requests and send them to the SRQ of the right process. This way, you really decrease the number of overall queue pairs you need, bringing it down to the number of nodes times the number of processes. Okay, so moving on to the RDMA verbs. The verbs is actually the abstract definition of the functionality that's provided by an RNIC. It's like the API. The operating system will provide an API for this verb definition based on what the RNIC supports and what the OS wants to expose. And the API or the verbs are the same for all wire protocols. So it doesn't matter if you're over InfiniBand, over Ethernet, over iWarp, which is over TCP, you'll have the same verbs and same API, meaning same application will work on all. We separate the verbs into two groups. We have the slow path verbs, which are mainly used for the configuration and the setup and initialization of the application. So you have the device-related operations, where it's just opening and closing and getting a handle to an RNIC, an RDMA NIC device. A protection domain would be allocated and deallocated and then used in the rest of the operation of the verbs, moving on to be part of the protection domain. A memory region is registered and deregistered, and a queue pair is created, destroyed, or modified. So modifying the queue pair, for example, can be modifying its timeouts or the number of retries you want to do on sending packets. And you can have different states of the queue pair where you can modify different parameters. And the CQ, the completion queue, again, you can create it, destroy it, and resize it. And the shared RQ, as mentioned, also can be created and destroyed and will have to be created before a QP if you want a queue pair to use the shared RQ. So these are the slow path verbs. Moving on to the fast path or the data path verbs. This is where the RDMA magic happens, right? So until now, all the slow path verbs, of course, it's all done on the host using the host CPUs and cycles and kernel and everything, privilege driver to configure. But now with the data path verbs, this is where either a user application gets direct access to the RNIC, and where the RNIC can start accessing the memory and performing the DMAs with bypassing kernel and CPU usage. So fastpath verbs are, if we talked in the very beginning about the two groups of operations of channel semantics, send, receive, and then the memory semantics for the RDMA operations, then the send operation means you're sending a message that will consume an RQ on the peer. And the receive operation means that you're posting an RQ buffer to ensure that a send that is received is handled, has buffer to be handled. And when you write an RDMA application, the RDMA application needs to ensure that you don't perform a send before you know that the target has already posted a corresponding receive buffer to accept that. RDMA operations, which is RDMA write, RDMA read, and atomic operations. These are, of course, also the fastpath verbs. And there are also some fastpath memory operations that you can do. So I mentioned that the memory registration is a slow path verb, but you can, for example, there's a memory window that you can bind as a fastpath operation, meaning that you're only providing access to a specific part of the memory region. And this binding of the memory window, it gives another level of protection for your memory regions if you just want to give temporary access to a specific process. And it can be done on fastpath. And another fast data path verb is the fast register MR. This is where you already have pinned addresses and you want to register them in a faster way. It can be done by privilege drivers. This is usually done by their kernel upper layer protocols. which are privileged and can do this operation in fastpath mode. Okay, so now hopefully we have an idea of what the objects are, of how a connection looks and what the API is. And now I'll try to put this all together and show you how an application would typically look, a simple one, and what goes on the wire while you're doing application operations. Okay, so the typical application stages, you start off with the host initializing some context and registering some memory regions you want to read and write from. You then establish a connection. Then using a send-receive model, you'll exchange memory region keys. So when we talk about memory registration, we said we have an L key and an R key. This means a local key for accessing your memory on your host, and an R key which you got using this exchange method, which points to a memory registered on the peer. And then after we exchange memory region keys, we can post and read write operations, right? The RDMA read and write operations. So now we'll go into each one of these steps. We'll see what happens in each one of them on both a client and a server application, and we'll see what happens on the wire. So we start off with no objects created, nothing happens. We're starting off with the host initialization step. So on the this can be a server client or a target initiator, but can be also be tools. Same application to application. That's just for making things a bit more clear on what happens. So on the server side, we'll create some RDMA event channel, which will be used to receive RDMA CM events. So these events can be, for example, a connection request that comes in or a notification that the connection has been established. We then bind to an address and we create a listener on the target side waiting for connection requests from some client. On the client side, we also create an event channel. Here, the RDMA events may be a bit different, like we'll get events that an address has been resolved and that we can do the connect. And also, we will get the connection established notifications. We create a connection identifier to handle this connection. We resolve the peer's address and we try to resolve the route to the peer. And then before we do the connect, we create the objects, the RDMA objects, the QP, the CQ, the PD, before we try and connect. So after this stage, after the server is just listening, no objects have been created. The client has created a few objects. This is our current state. Okay, so client has a QP and a CQ. It may have already posted some RQ buffers to the QP to prepare for once the connection is established and getting send requests from the server and configure the RDMA NIC accordingly. Next part of the initialization. So now, if we look on the red, we'll start on the client side, on the right side. So the client is now sending a connect request and waiting for the connection to be established, waiting for an event saying the connection has been established. And on the server side, we're waiting for a connection and say we now got the connection request. So once the connection request was received, then the server creates a PD, a CQ, and a QP. It accepts the connection request and also waits for the connection to be established. Once both sides get the established event, then they can start posting operations as appropriate. So this is our state after the first stage of the initialization. Both the server and the client have a QP, a CQ, perhaps also already a memory region, which it wants to soon start exchanging the keys, perhaps some RQ buffers that have already been posted to the Q pair. Now let's take a look at how all this looks on the wire, just the connection establishment stage. So with the connection setup, we have, like I said, it's an out-of-bound connection setup. So we have a specific QP for this method for InfiniBand and RoCE called the GSI QP1. This is a source and destination QP1. That's the identifier. So say we have the initiator has a local QP number 100 and it wants to connect to the target, then it sends a connection request. On the connection request, it writes that the destination QP and this is a UD QP. Okay, so It sends it the destination QP and the source QP is 1, and it sends a MED, a management datagram. Okay, so the management datagram is a type of message that's used for managing and configuring the connections. And there are some management datagram operations that are performed on the GSI. Then you get a connect reply from the target to the initiator, also saying this is SQP, source and destination QP1, telling you what's the IQPN of the target side and the communication ID for handling this connection. So this is like a three-way handshake. So the other message, the MED message, another management datagram, is ready to use. So once the initiator got the connection response, it sends a ready to use. Now the server knows that there are also RQ buffers already posted because it got the ready to use. It can do send commands, and now it's time to exchange memory region information. So this is actually how it looks on the wire. This is RoCE, and it's used Wireshark trace to show that you can actually run this connection establishment and see the actual packets that I showed with the management datagrams on the wire. So we'll see the connection request replied and ready to use. And if you look at the packets themselves, then you can see that we have, this is RoCE, so it's over IP, UDP, and then you have the InfiniBand headers, and marked in red shows the MAD header operation, right? Connect request, reply, and ready to use. So back to our drawing. Now we have connection established, and we want to go to the second stage, which is using the send-receive model to exchange memory region keys between the peers. So say the server application has a yellow S buffer on the left and has this yellow R key, which was received by the RNIC for accessing this S buffer from a remote application. On the right, we'll have the C buffer in orange and an R key representing that, and we want to exchange these keys. We want to exchange them so that they can do operations, RDMA operations using them. So the operation that will be used here is a send operation. We'll have to prepare an SQ buffer, which contains the information of the key, place that in an SGE on the operation, and send it to the other side. So we're using the send operation here. So let's take a look at how send looks on the wire. This example is an 8K send, so it's much larger than just a key exchange, but it can have additional data that you want to exchange. And we're showing, like, for example, you want to send 8K using 2K MTU. Okay, so the initiator will have to send, this is on the wire, right? So the initiator operations of the send is different for the first packet and the last packet. And you can actually see on the wire that you'll have a send first, send middles, and send lasts. Now, because it's a reliable connection and it's an ordered connection, then you can ask not to acknowledge the first packets of a message. So you can see here I marked in the fields that acknowledgement is 0, and only the last one is acknowledgement 1. This means that the target can send just one acknowledgement for the PSN4, and then the initiator will know that the entire message was received on the other side. And now let's see how it looked on the wire. So as you can see, this is a 8K but with 1K MTU capture. So in the blue, you can see that we have the send first, all the middles, and the last, and the acknowledgement for these packets. And on the left-hand side, you can see open the base transport header of the InfiniBand, which contains the opcode, first line under the base transport header, which is saying it's a reliable connection, and this is the send first packet. Okay, so now we've exchanged the keys, and the server application has the orange key and the client application has the yellow key. And now we want to start performing the read and write operations, which can be very large operations that bypass the CPU and kernel stack. So the server application, for example, will perform a write operation. It will provide in the WoKey the remote key and the address that it has. It will also provide the local key address, right, saying to the RNIC where I want to write from and where I want to write to. So on the left and on the server, the RNIC will DMA the buffer directly, the entire size, to its internal buffer, packetize it, send it to the other side. and write it to the client C buffer application without involving CPU. And this all is done using the R keys that were exchanged in the previous stage. So now, if we've already seen how the other operations look on the wire, let's see how the write operation looks. So 8K write operation using 2K MTU. Also, same idea. We have the write first, middle, and last packets. We'll just have an acknowledgement for the last one. Now, if we look at the capture, then what we can see is, as opposed to the send, an additional header that is passed for the RDMA write is the RDMA extended transport header marked in a blue box on the bottom left. And this shows here that it contains the information of the remote key and the virtual address on the remote side and the DMA length. And in red, you can see again, I'm repeating the concept that not all packet needs to be acknowledged. So the first one's acknowledge requests are false, and just the last one is the true. And then the small blue boxes show that we have also here the first, middle, and last packets. Similar to how we perform an RDMA write, we perform an RDMA read. The main difference is that with RDMA read, there's always first an initiator request saying that it needs to read the data from the target, and the target is the one pushing the response packets back to the initiator. Okay, so it goes with the first and the middles and the lasts once again. And to be complete, I'll show the wire shock of the read. So as you can see here in the blue rectangle, first operation is the read request, and then you get the responses. And also here on the packet itself, it will have an RDMA extended transport header similar to the RDMA write.
I
And
just
now,
want to
yeah,
just want to jump in. Sorry, Mikhail. I know that
yeah, sure.
there are some great questions coming in. Please keep them coming in. I just know that based upon where we are in the presentation, we're going to probably run really close to the top of the hour. So, but keep them coming. We will answer them, as I said, in a blog post after the session wraps up, and appreciate the engagement. So sorry, go ahead, Septania.
Yeah, so to talk about transports and congestion control, I'm giving the handle back to Rohan. So thanks.
Thanks, Mikhail. So yeah, let's take a look at some of the most three common RDMA transport protocols, InfiniBand, RoCE, and iWarp. You can see how the layer 2, 3, and 4 differ for each of these protocols. If we keep the RDMA data, the CRC, and the checksum part common, you can see the header structure essentially just differs from the layer 2, 3, and 4 headers. So iWarp, for example, has Ethernet and IP header followed by a TCP header. RoCE has Ethernet, IP, and a UDP header. InfiniBand comes with its own set of definitions, which is something called LRH and GRH headers, and then followed by the RDMA data, CRC, and checksum. I want to focus a little bit on our RoCE, particularly RoCE v2, because it is the most widely deployed protocol out there for RDMA today. Some of its best features today, one of the best features today it has is layer 3 routing. So because RoCE v2 has the support for IP packet, both IPv4 and IPv6, it allows RDMA traffic to traverse layer 3 networks, be routable. This is a major upgrade from RoCE v1, where it did not have routing capabilities. The UDP encapsulation ensures that you're not bound by the strict reliability requirements of TCP, but you can still do large swaths of data transfer based on whatever MTU size you define for your version of protocol, in your send queue or in the bookie element of your send queue and receive queue. RoCE provides high performance and low latency at the adapters, so at the NIC level. Typically, if you look at the line rate latencies, they are of the order of 1 to 5 or 1 to 10 microseconds. That is really fast. But the key element here is that RoCE requires lossless Ethernet network to achieve this low latency operations. So this means that the Ethernet switches in your network fabric, they will need to support something called data center bridging and priority flow control, which are mechanisms that basically facilitate lossless traffic to be maintained. RoCE packets are very susceptible to packet losses, so it's a tricky mechanism to configure your switches in a way where the lossless traffic is ongoing, but you're still not facing any packet loss. And in order to do so, you will need some very robust congestion control mechanisms, which I'll talk about in the next slide. Very recently, nowadays, there's something called soft RoCE, which has been developed. It emulates a RoCE protocol in the software, which can be useful if you don't have the RDMA hardware or RDMA infrastructure in place. It's important, obviously, because it's a software. CPU will be involved, so you won't see as much CPU benefits as you would with typical RDMA on RDMA hardware and RDMA capable switches. And there'll always be some latency costs also associated with that. Moving on to congestion control. Yes, as I mentioned, congestion control is really important in RDMA networks because RDMA network fabrics are really susceptible to packet losses. There are several mechanisms out there. I'm going to talk over a couple of them, which are more important, and then breeze over the remaining because they are important as well. It really depends on what your use case is, and how prevalent that particular congestion control algorithm is as of today. So priority flow control is a layer 2 flow control mechanism that prevents packet loss during congestion by pausing the traffic at the specific priority level or the specific priority class. So traffic is usually assigned a class, and then if one particular class is seeing a lot of traffic, you send a pause frame back to the source, and that will essentially prevent any congestion. You will tell the source to slow down and prevent any congestion. PFC is extensively used in RoCE v2. It is optional for iWarp. DCQCN, or data center quantized congestion notification, it's normally you can say DCQCN equals ECN plus PFC. So ECN is explicit congestion notification, which is a flag typically available in TCP, and you add PFC features on it to dynamically adjust the traffic rates on network link based on the congestion feedback. So PFC, as we discussed, manages the data flow at the interface level or at the class level, whereas ECN detects or mitigates any congestion before PFC activation becomes necessary. So ECN is something that can be sensed from the destination to the source. The key here is to isolate that the ECN flag coming in is for a particular source, so for a particular culprit source, so that you don't end up pausing an entire link and all the other sources that are also sharing that link. DCQCN is widely used today in storage networks. Robust congestion control, RoCE, leverages switch queue sizes to compute fair data rates. So it's basically the congestion control deployed at switches. You keep a track of all the queue sizes, and then you start sending out PFC frames based on whichever queue size is close to maximum limit. The goal here is to ensure stability, rapid convergence, and fair throughput, because at switch level you are agnostic of what the source is, so you are only targeting the source whose queue is very full or close to being full. Shape quota is a method that allocates bandwidth quotas to different traffic classes and active connections, and ensures, again, fair distribution and fair sharing of the network bandwidth. This is done by the receiver. So receiver says, I have X number of sources. I'm going to allocate bandwidth to each of them and adjust them dynamically based on who sees more traffic and who sees less traffic. Because this is receiver driven, there is no concept of PFC involved here, and so it requires some form of retransmission to maintain reliability, or to take care of packet losses. Round trip time congestion control, RTTCC. This is something relatively new. Uh, Basically, what it does is dynamically adjust the transmission rates based on the round trip time measurements or an average of round trip time measurements over a window to enable efficient and scalable congestion control. RTTCC is largely used on compute side because compute is where uh, you can have more latency sensitive applications, and the best way for the such applications to figure out what to do in the situation of a congestion is to just measure the round trip time and predict if the round trip time keeps on increasing, so you can predict some congestion control responses for that. Let's talk about some use cases. There are many use cases for RDMA. Storage, compute are definitely the main ones. So whether it's in on-prem or cloud storage, RDMA is really helpful in redundancy, disaster recovery, scalability. Apart from performance, all of these features are also benefit from RDMA. All of these metrics also benefit from RDMA. Various file systems are now supported over RDMA fabrics, so you can have extensible on-prem clusters or even hybrid cloud solutions, depending on what file system you're using. If you just want to modernize your network fabric, you have some age-old typical Ethernet fabrics. RDMA would be the next in line, or the next thing to do, next step to take to upgrade your network fabric. Supercomputers, many of the top 10 supercomputers today use InfiniBand network stack. Supercomputers are actually the first adopters of RDMA, and they still rely on it. Even the modern ones that are being constructed use RDMA or InfiniBand exclusively. And of course, AI training and inference, which happens through lots of neural networks and various layers inside those neural networks. You're essentially traversing them from one compute to another compute. And so RDMA in these situations would help you avoid any unnecessary copies of data as you're going from one layer of a neural network to another. There are many enterprise-grade benchmark workloads like SAP HANA, SQL, or NoSQL databases, ERP, and enterprise resource planning. The ETL, this is one of the great benchmarks that are separated out for RDMA and TCP workloads. These are some of the workload benchmarks that you can refer to based on your use cases to see whether you can benefit from RDMA. The next two slides, they have a potential to be an entire webinar by itself. I'm going to try to be as quick as possible, given we're close to completion. So I'm going to talk some use cases on compute side, where the benefits of RDMA can be read. You can start with figuring out where your application is. Is your application in a VM or in a container? Do you want to leverage RDMA right where your application currently is, or are you ready to move your application around? Applications and VM, if you want to be in VM, you can leverage SRIOV, so single root IO virtualization, to talk directly to the physical network or to the RNIC. You can skip the hypervisor. Containerized applications are anyway built for bare metal performance, so you can talk directly to the RNIC across PCIe. You might want to figure out what your application, how many layers your application has to traverse before communicating to the RNIC, to the physical networking device. How many of these layers are in user mode? How many are in kernel mode? Typically, the RDMA driver or the RDMA firmware lies in the kernel mode, so you would want to get to the kernel mode eventually, or possibly as fast as possible. So your application needs to find a proper solution on how you can transition there. Once you have this mapped out, you can then figure out how you can modify your application based on what you learned today. So can I leverage the send and receive queue pairs right inside my application, or do I need another layer in between to do so? If you're a very large scale application that spans multiple compute SKUs, It might make sense to invest in writing this middle layer, something like a filter driver or something that can abstract away all the differences and limitations for the different compute SKUs and make your application available some generalized form of APIs so that it's easy to scale your application that way. Um, Note that here in this example, it is agnostic of whether the application is talking to a storage server or another application running on another compute or even a GPU. Based on whatever your use cases are, you would want to adjust how your application talks to another application as well. There are many other scenarios. I'm going to quickly skip over to the last slide here, which is the storage protocols. There are many cases for use cases for storage as well. Let's start. Say you have an on-prem storage solution that is completely based on NVMe. So you want to figure out, can your NVMe host interface use the submission and completion command queues that NVMe has built in? Can you use those as a send-receive queue pairs to talk directly to RNIC? You would want to pay some attention on how you use them, because NVMe already provides lots of massive parallelism by breaking down a large task into smaller tasks across PCIe. So you might not want to do the double work. You just have your submission and completion command queue work as send and receive queue if possible. If your scenario is scaled out to a cloud-based environment, you can use NVMe over Fabrics over RDMA to transfer messages between multiple storage servers or between a computer and a storage server. Note that when you're using NVMe over Fabrics, the host reads or writes don't actually use NVMe submission or completion queues. The data comes directly onto the RDMA NIC. It's on the target side, the destination side, where the real NVMe submission and completion queues come into play. So again, if you're talking from storage to storage, you might want to do the work only on the target side to develop the NVMe or create the NVMe submission and completion queues. If you are a storage solution provider yourself, you can think of ways to save your customers compute resources, like the way we discussed today, and you can take ownership of pushing and pulling your data. What I mean is that when an application on a compute wants to read something in the backend storage, the storage server takes the responsibility of finding the data as well as writing it onto the remote memory of the compute application, and vice versa. So if your application wants to write something to the backend storage, you pull the data or read the data from the remotely from the compute memory and commit the data onto the backend storage. In doing so, obviously, you would want to take care of security aspects. Special attention needs to be paid because you can RDMA read and RDMA write. You would want to have a proper authorization and authentication steps in place before you actually do this pushing and pulling of data remotely. There are many other real-world use cases that can benefit from RDMA. We really hope that this webinar helps you to get started figuring out what your application needs, what your infrastructure layout currently is, and how you can leverage RDMA to get the most out of your application. Key takeaways. So this is I'm going to just recap what we went through today. We learned about RDMA and its benefits. Apart from low latency and high throughput, it lets you bypass the kernel networking stack by using something called zero-copy networking, making your application as fast as possible, making you achieve almost the line rate of throughput. We learned about RDMA objects, so queue pairs, CQ, completion queue, send queue, shared receive queue, protection domains. And then we learned how, in a typical application, you can use these RDMA objects to create your application, modify it, and make it capable for RDMA. We learned how an RDMA packet looks on the wire. And then we discussed about some of the use cases on compute and storage side.
All right, thanks, Rohan. As I was concerned, we are out of time. We have like 23 seconds left. So we'll wrap this. We will answer the questions. Thank you again for everybody who submitted questions. They're great, and look forward to answering them. Just a reminder, please rate the webinar and provide us with your feedback. And again, we will be posting that Q&A to our blog at sneablog.org. So thank you again for attending. I hope this was worthwhile, and look forward to talking with you in the future. Thank you.